I wanted to start with a brief introduction on the objectives of this webinar series. The picture that you see here is a cloud seeding aircraft on a mission. And the picture also shows a cloud, which is very complex. You see cloud droplets that are supercooled. You see ice particles. You also see different cloud layers. But you also see a very mature thunderstorm that the aircraft is trying to target. In order to perform weather modification, and in order to study these type of clouds, the first thing that we need to understand is their microphysics. One thing is very well known is that all cloud droplets form on aerosol particles. These we call cloud condensation nuclei. We also know that ice crystals form on aerosol particles or from the cloud droplets that formed on aerosol particles. So these are the IN or the supercooled CCN that then act as ice nuclei. These particles are also interacting with each other, and in order to understand these interactions and to target these clouds for cloud seeding studies, we need high quality measurements. These are critical in the understanding of aerosol cloud interactions. Next, I want to introduce the speakers and presenters for this webinar series. In a few minutes, you'll hear from Dr. Daryl Bogmardiner, who founded Droplet Measurement Technologies 32 years ago. He is a PhD from the University of Wyoming in atmospheric sciences, and he's the chief scientist at Droplet Measurement Technologies and had previous appointments at the University in New Mexico and also almost 20 years as scientist at NCAR, the National Center for Atmospheric Research in Boulder, Colorado. He is very well published, more than 200 publications, and has received awards for these publications, and he is an internationally recognized expert in aerosol and cloud measurements. You will also hear from me later in the webinar series when we start talking about aerosol cloud interaction feed campaigns and weather modification studies. My position at Droplet is Director of Science Programs and Research Applications. And prior to Droplet, I was a scientist at NCAR for 10 years. And you will also hear closing remarks from the President and CEO of Droplet Measurement Technologies, Dr. Jeff. Jeff is a global technology leader and has extensive international experience dealing with instrumentation and commercialization of new technology.
Well, while Duncan is doing that, I'll go ahead and begin introducing the topic of today. I will be giving 5 talks, 3 in the next few days, and then 2 more on Monday and Tuesday. And what I'm trying to do is cover a lot of topics having to do with cloud microphysics. Okay. Looks like, can you see my screen now? Okay, that's good. Let me get the full screen here. So I'm listing here what I'm hoping to accomplish and the objectives of the first 5 talks that I'll be giving. And what I want to do is highlight the role of clouds on the environment, to give a brief tutorial on cloud microphysical processes, and then finally my little presentation will be to talk about the research tools that we are using to study these processes. So first of all, I would like to apologize if some of the material I present is familiar to you already. I don't know who all I'm talking to, how many of you are meteorologists, engineers, students, So I've tried to prepare the material to provide enough detail to explain the material without being too simplified, but I also don't want to be too complicated. So the motivation for cloud studies in general, of course, as scientists, we are basically curious. We want to know more about the environment around us. We want to understand how things work. And so studying clouds is part of that process. Secondly, we would like to improve our understanding of how clouds impact the hydrological cycle. Following that, we know that forecasts of climate change right now are not as good as we would like them to be. And to better understand clouds is to better understand forecasts of climate change. So, fourth, we'd like to improve weather forecasts, especially of extreme events that affect human activities. And finally, because a lot of you are in the weather modification business, you understand that to understand cloud properties is to better understand how to modify weather and also how to mitigate climate change. Okay. So briefly, let's take a look at how cloud properties, and in particular hydrometeor characteristics, have an impact on the environment. So first of all, for climate change, cloud albedo, in other words, how do clouds reflect radiation, is important for climate. And the hydrometeor characteristics are the number of cloud particles, both water droplets and ice, how much surface area there is, what is their scattering phase function, and also what is their extinction coefficient. But the lifetime of clouds is also, of course, very important for climate and for weather and for hydrology. And the lifetime is impacted by the number and the mass and the fall velocity of the cloud hydrometeors. The spatial distribution of the clouds, again, this impacts climate and weather. And of course, precipitation efficiency and rain rate is very important for both climate and weather. And the last that I won't be talking about, but Duncan will be talking about, is how efficiently do clouds process the chemistry of the atmosphere. And again, this is extremely important for climate and hydrological cycles. So in this talk today, I'm going to try to focus on 4 points. I'm going to talk about the key points of the 2013 report of the Intergovernment Panel on Climate Change that came out actually in 2012 and 13. Then I'm going to talk about direct forcing of clouds and the sensitivity of this forcing to microphysical properties, followed by the challenges that we face in our community, proving how clouds are represented in climate models. And then I'll finally end the presentation today to talk about clouds, weather modification, and geoengineering. So the reference here that I'll be using is Boucher et al., and this is part of the 2013 Fifth Assessment Report to the IPCC, in particular, Chapter 7. So I think this figure from that report shows extremely well why clouds are so important to climate change. Because of clouds' interaction with solar radiation and also with the infrared radiation from the Earth, the fact that they cover, on average, at any given time, 2/3 of the globe, as shown by this picture here, which is a composite satellite picture. Here we see the scale at the bottom. It's a color scale showing the fraction of clouds or the fraction of type of clouds going from 0 to 1. And we see that practically every portion of the globe is covered by some type of cloud, some fraction of the time. We can see over here on the right top graph that the type of clouds, be they liquid or ice, depends very strongly on the latitude. So in the equatorial region, where we have the tropics, the highest frequency of clouds are in the upper atmosphere or the lower troposphere, as shown here. As you move to the mid-latitudes, more of the clouds are low-level clouds, like these stratus clouds. And then as you move into polar regions, they cover a wide range of altitudes. So this is just a very quick picture of the importance of cloud coverage and why it's so important that they are represented properly in the climate models. So reminding you of how clouds interact with the radiation, solar or infrared radiation. Clouds, of course, can reflect back to space the shortwave radiation, and some of that radiation, depending upon the thickness of the clouds, can be retransmitted and scattered by multiple scattering down to the Earth. Likewise, clouds can emit radiation, so clouds can also absorb infrared radiation or transmit infrared radiation. So all of you, I am sure, have seen this figure that came out of the 2007 assessment by the IPCC. And it's a very important, although detailed, description of how different atmospheric components force the climate through radiative forcing. So on the left column, these are the actual forcing terms. We have the greenhouse gases and ozone, water vapor, as well as surface albedo. And down here we have aerosols and clouds. In the middle here, we see if the forcing is positive to the right or negative to the left. And we see, as we know, that the greenhouse gases cause positive forcing because of the absorption of radiation from the Earth and basically trapping that radiation and leading to warming. But aerosols and clouds have the opposite effect most of the time. In this case, they are actually causing a generally cooling effect. So if we go over, we can look at how the scales are as far as their geographic scales. Of course, greenhouse gases are global, but aerosols and clouds tend to be more continental, but they can also be global. But the final column is the most important column. This tells us what is our current scientific understanding. How well can we predict the forcing caused by these different components of the atmosphere? And the important thing to see here is that even the most recent report, the scientific understanding is low. That means there's so much more that we have to understand about clouds. So we need to be able to better understand how clouds are used in global climate models in order to lower the uncertainties. So before I go on, let's talk a little bit about the difference between clouds and aerosols. We have certain definitions of what a cloud particle is and what an aerosol particle is, but there is something that is called a twilight zone. This is actually that zone between the cloud-free atmosphere, what we think is cloud-free out here, that blue sky, and the cloud. So this is from a publication by Corinne et al. In 2007, where they show that the area between clouds and aerosols is not so certain. So they have taken a camera image and they have filtered it so that you can see the so-called cloud here, but you can see that around the cloud there is this haze that actually extends the impact, radiative impact of these clouds for tens of kilometers beyond the cloud itself. And this is an earlier study in 1991 where measurements were made from an aircraft of clouds, as shown here in dark, water vapor, shown here in the dark line, and condensation nuclei in the dashed line. And what you see here is that actually, away from the cloud, you have very high concentrations of aerosol particles beyond what you would have out here in the cloud-free zone. So this is just additional evidence that you have clouds impact here on the outside. So the representation of cloud processes in climate models have been recognized for tens of years as the dominant source of uncertainty in our understanding of changes in the climate system. Secondly, we know that clouds respond to climate forcing mechanisms in many ways, and the differences in cloud feedback constitute the primary source of spread in both the equilibrium and transient climate responses. So our confidence in climate projections requires a thorough assessment of how climate processes have been accounted for. So there is a real symbiotic relationship between climate, aerosols, and clouds. As shown by this intersection plot, we see that aerosols impact climate by the direct effect. In other words, aerosols reflect solar radiation in the direct effect, and clouds also have a direct effect reflection back to clouds. But climate, because we have warming oceans and melting ice and increasing deserts, that feeds back into the cloud formation. Likewise, because of warming climate, more deserts, we have desert dust, more salinity from the oceans, and less phytoplankton to form the aerosols. So this is kind of the big picture. But now I'm going to take you to a much more detailed diagram that is at the essence of the Chapter 7 report. I'm going to take a little bit of time with this diagram because this really shows you all of the important interactions between aerosols, clouds, and radiation. All of these feed into the global surface temperature, which is what is causing the changing climate. So, first we have what we call our forcing agents. In this case, our forcing agents are aerosols and the greenhouse gases. And the way that they're forcing is through the aerosol radiation interactions and radiative forcing. We also have aerosols that are interacting with clouds and clouds that are forcing into radiation as well. And this is all feeding back into the global surface temperature. Now we have to take into account that this forcing is constantly and very rapidly being modified by adjustments whose pathways are independent of what's happening here. What this means is that despite what's happening in the global surface temperature slowly, we can have clouds forming fairly rapidly on timescales of hours to days, and the aerosol fields can be changing very rapidly. So the climate models have to take into account these adjustments. So this is a big change from the report in 2007. In 2007, they were not taking into account these rapid adjustments. And then we have to look at the feedback pathways. So these curved arrows here, these show the feedbacks that come from the changing global surface temperature. So the global surface temperature feeds back into the atmospheric moisture and winds, vertical temperature profiles, regional variability, and also changes in the biosphere. And those changes go into changing the characteristics of the aerosols, changing the characteristics of the cloud, and changing other properties of the atmosphere that feed into the radiation. So the question is, why is it so difficult to represent cloud processes in global climate models? Figure also from the chapters 7 is a beautiful example of many different types of clouds occurring all at the same time. So on the left-hand side here, this is a satellite image that's covering more than half of the globe, from the poles north down to the mid-latitude to the south. And all these different cloud fields you see here are representing a number of different high-level, mid-level, and low-level clouds. On the right-hand side here, in figures 1 and 2, these represent cross-sections across these clouds here in orange, and below in red, these clouds here. And what you can see going from the mid-latitudes here, we have stratus clouds in this area. They move into nimbostratus and cirrus clouds here. And then in the polar area, we have mixed phase stratus. Likewise, going from the deep tropics here to the subtropics here, in the deep tropics, you have these convective towers that are pushing moisture up into the upper atmosphere. And then as we move further south, we have the trade wind cumulus, shallow cumulus, and finally stratocumulus down here around Chile. The point of this is that apticenters show that more clearly that low clouds are prevalent in nearly all types of convective systems, and these are very often underestimated in the models. And it also shows that having these many layers presents a real challenge to global climate models. So this is something that really has to be taken into account. But representing the microphysical properties is even a bigger challenge. So if we first look at warm rain formation, we look at the scale across here, and this scale from left to right is probably maybe only 100 kilometers. Okay? And global climate models typically will have cell sizes that'll be anywhere from 50 to 100 kilometers, which means processes like this might be happening in the single cell of a global climate model. And what we see that we have convection that's bringing cloud condensation nuclei from the surface boundary layer. These activate to become cloud droplets. They are then vertically transported, they grow, and then the cloud evaporates and gases and aerosols are detrained, new particle formation. These then circulate back down into the boundary layer where they once become clouds, and they change the properties of these clouds. So the question is, how do we represent this type of mechanism in a global climate model? Ice formation gets even more complicated. And the reason is because there are multiple ways that you can form ice crystals. So you see here that you can have CCN that are coming into cloud droplets that turn into ice, or you can have aerosol particles that go directly into ice. And to see this a little bit more closely, you can see that we have at least 5 possible ways of forming ice. One is where you have aerosols become cloud droplets. The cloud droplets go to temperatures less than minus 38 degrees, and they freeze. Or you can have aerosols that go directly to ice. That's called deposition nucleation. And then you have 3 other types of ice production that's called immersion, condensation freezing, or contact freezing. So very complicated. And yet, how can we represent these in global climate models when at the moment we don't even understand how all of these formation mechanisms work in real clouds? We can duplicate them in the laboratory, but trying to put them into models is a much more challenging affair. So in summary, on a 50 to 100 kilometer scale, the same type of scales that are being used in models, we can see that all of these processes, precipitation, aerosol scavenging, ice formation, new particle formation, scavenging by droplet coalescence, ice nucleation, all of this has to be represented in cloud models. And this just gives you an idea of what type of models are currently being used and the spatial and time scales over which they are being run. So for cloud processes, microphysical processes, the spatial scales have to range from anywhere from a meter all the way up to tens of kilometers. And the time scales have to go from minutes to days to months to weeks to months. But for global climate change, for climate models, the climate models have got to find a way to incorporate these cloud processes in them. And this is where the challenge is. Okay, so I'm moving on now to the last 2 topics that I wanted to talk about today. One of them has to do with weather modification by cloud seeding. And as weather scientists, many of you are working on cloud seeding to do enhanced rainfall, enhanced snowpack, mitigation of hail, and also to decrease pollution, very much like was done during the Beijing Olympics. So we know that cloud seeding is possible. As early as 1946, a project called the Cirrus Project was conducted by the General Electric Company, spearheaded by a team of scientists, Irving Langmuir, Vincent Schaefer, and Bernard Bonniet, and they were seeding stratiform clouds with dry ice, frozen carbon dioxide. They were putting the dry ice into this aircraft here, and they just dispersed it into the stratiform clouds, and there was a very clear effect, as you can see, by these blue arrows. But isn't that easy? So when the modification is a challenge, there are literally hundreds of possible pathways that can lead to precipitation. And the question is, where in the cloud is the best location to see? Do we do it at cloud base, or just above cloud base? Or do we do it at cloud top, or just below cloud top? And then not only is the location important, but the timing is very important. If we see too early, we might have the effect opposite of what we want. If we see too late, then the chance to do the change of the cloud properties may be too late. And also, do we seed with glaciogenic or hygroscopic material? So, for example, for hail suppression, there are at least 4 alternative microphysical pathways that can be altered. We know that hail forms from supercooled water that can either form into drizzle droplets and then grapple, or it can freeze into ice crystals into grapple. So, which of these pathways are we going to try to break with our seeding? There are 12 microphysical pathways that can be altered for doing rainfall enhancement. You can just look at the different processes, the different pathways, and see that we can get to raindrops through any one of these different pathways. Which ones of these are we going to try to change in order to enhance precipitation? Likewise, with snow augmentation, we can have 8 different pathways. So there are many problems. First of all, the cloud droplet and ice crystal nucleation processes are still not that well understood, except for the simplest of nuclei. And you know that the heterogeneous nucleation of water droplets is a function of composition. How there are many different compositions in aerosol particles, and many of the aerosol particles, we just don't know if they're good cloud condensation nuclei or not. Ice nucleation is even more complicated than liquid water nucleation, since, as I showed you, there are at least 5 different types of nucleation. And finally, the processes of coalescence, liming, aggregation, and ice multiplication, these are topics of research that still require a great amount of effort in order to better understand how they actually function, how they actually work in the natural environment. So we must understand basic cloud microphysics processes, or there is no hope to modify clouds artificially. And that requires, as Duncan said, high quality measurements with complex instruments. And lastly, I wanted to touch just briefly on geoengineering by cloud seeding. As the same previously, climate change is a major issue and a major topic of research. And one of the things that's being explored is geoengineering as a way to deliberately alter the climate system in order to alleviate the impacts of climate change. There are 2 distinct categories of geoengineering methods that are usually considered. One is solar radiation management, and that's designed to offset the warming from anthropogenic greenhouse gases by making the planet more reflective. The other method is carbon dioxide removal, which aims at reducing atmospheric CO2 concentration. So the models suggest that if solar radiation management methods are realizable, if they're effective, they could counter increasing temperatures and could be effective in countering some other types of climate change. Now, we know that we can actually artificially brighten clouds. For example, you all have heard of ship tracks, and you have certainly seen on satellites ship tracks. These are these clouds here. And these are just clouds that are being seeded from below by ships that are emitting particles from combustion. And these particles are high concentrations of CCN that form small water droplets that reflect sunlight more effectively. And this is why these are brighter. And so, as I said, the models seem to indicate that if solar radiation management methods were applied, they could offset changes in temperature, shown here, the dashed line, of carbon dioxide emissions that increase at 1% per year. With solar radiation management, the models say that we could flatten this curve down to zero for at least 50 years. And in fact, there are proposals that have been put forward to do such brightening of stratus clouds, to actually float platforms that would take seawater and evaporate the seawater and inject salt particles, CCN, into the atmosphere to form low-level stratus clouds, marine stratus, that would then brighten the Earth. And there's actually a very large group of scientists worldwide working on this, and you can find more about it by going to this website, mcbproject.org. So this concludes my presentation for today. Tomorrow I will get more into the details of the microphysics of clouds and focus on atmospheric thermodynamics and cloud dynamics. So I think that that is a good place for me to end my presentation. And let's see if I can stop sharing.
对，各位专家如果有问题的话，现在可以提问。
Thanks, Terry. And I'm originally come from the Zhejiang University. I have a question. I missed your talk because I have a class. So I have a question about the air pollution in China. How is there are lots of the black carbon? I'm thinking how is the possible the black carbon influence the cloud droplet? Is that you have any information or suggestion? Because in the future we will using CVI to collect some cloud droplet to do the aerosol, the cloud single droplet. Yeah.
Yes, thank you for your question, and that's a very good question and very relevant to China, of course.
Yeah.
The project in 1999 called INDOX actually looked over the Indian Ocean at that very topic. And what they found is that black carbon can actually lead to the dispersion of cloud or decrease the lifetimes of cloud. So what that means is that not only does black carbon absorb solar radiation and heat the local atmosphere, black carbon can also lead to decreasing the lifetime of the clouds that cool the Earth. So it has a doubly negative effect on warming the atmosphere.
Okay.
That means, we need more, definitely there's more research needed to understand the black carbon cloud interaction. Thank you.
Okay.
大家如果有些问题现场提时间可能来不及，可以写邮件给那个张宇或者张小拓都可以啊。明天我们呢待会会回答这些问题。
I think then we will draw this first session to a close. And please send any other questions that you have to Tracy at Shallow Sea. And Daryl, I think, will be happy to answer them at the start of the presentation tomorrow. So thank you, everybody, for participating in the first session. And thank you again, Daryl, for taking time to talk to us about the topics you have today. And we look forward to seeing everybody tomorrow.
好的，谢谢大家。Thank you, Daryl, for your excellent presentation.
Thank you very much.
好，那我们就明天见。